So let us see what we mean by the concept of the span of a set. So the formal definition, and we're going to use examples to make this a bit more real. If I've got a vector space V and I've got vectors in that vector space, the span of the set V1 to Vr. So yet again, the vector space V is not consisting entirely of V1 to Vr, they're just elements of V. So this set V1 to Vr is not necessarily a vector space, but the span of that set is the set of all linear combinations. And in the previous video, we looked at linear combinations and what that means. So if I look at a set of all linear combinations of a specific set, that's called the span of that set. Next concept, those vectors we say span the whole of V if, not all of those are in V already, but they span the whole of V if this set of all linear combinations of that set gives me V back. And we'll look at examples like that. So what this means, if every vector in my set V can be written as a linear combination of those vectors V1 to Vr, then we can say that set spans V. So let's look at our first example. All right, with linear combinations, we already looked at this example with I, J, and K. Where I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. Now, if we look at the span of set S, yet again, S is not a vector space, but let's look at the span of S. Span of S is a set made up of all linear combinations. So span of S is the set of all A times 1, 0, 0, plus B times 0, 1, 0, plus C times 0, 0, 1. Given, let's look at how we defined, where those coefficients A, B, and C are any real numbers. So I run through all the real numbers and I take all the linear combinations of those sets, and that's what the span of S look like. Now we said this set S spans the whole of R3. If I can take any element of R3 and it's in that span. So let's just look at some experiments. 4, 3, minus 2. That's any element of R3. It's not in S, but is it in span of S? Well, we know we can write 4, 3, minus 2 as 4 times 1, 0, and I don't have to put that in brackets, 4 times 1, 0, 0, plus 3 times 0, 1, 0, minus 2 times 0, 0, 1. So I can write 4, 3, 2, which is an R3, as a linear combination of elements of S. So that is also in the span of S. But now the question is, can any element of R3, so let's take X, Y, Z. That's an element of R3. We're not saying what X, Y, and Z is. Can I write it as a linear combination of elements from S? Yes, we can, because X, Y, and Z are all real numbers, and X, Y, Z is equal to X times 1, 0, 0, plus Y times 0, 1, 0, plus Z times 0, 0, 1, where X, Y, and Z are real numbers. So X, Y, and Z is also in span of S. So what we can say is this set S spans R3, meaning any element of R3 is in the span of S. So if I look at linear combinations of elements of S, then I get the whole of R3. Right. Now what if the vectors look a little bit different? 4, 1, minus 1, 2. Let's look at that set and let's see, well, the span of S is going to be linear combinations of those two. So A times 4, 1 plus B times minus 1, 2. Now we've looked at what linear combinations mean, so we don't have to look at. So all linear combinations that look like that. All right. So if I look at that set and I'm like, all right, we know it's a subset of R2. Do we know if this set spans R2? So what do we need to do? We need to say, let's pick an arbitrary element of R2. Let XY be an element of R2. Then what do we know about XY? Can I write? So we want to see, can I find an A and a B such that XY is equal to A times 4, 1 plus b times minus 1, 2. Now, there's way too many variables here. I've got a's and b's and x and y's. It seems a little bit strange. But what we have here, we can write as a system of linear equations, because if I look at the first entries, that means 4a minus b must be equal to x, and 1a plus 2b must be equal to y. So now I've got a system of linear equations. So look at what our question says. The question says, can I find this a and b? Not what is the a and b, because we don't know what x and y is. But can I find this a and b? Is it possible to find them? Well, it's possible to find them if this system is consistent, meaning if this system has a solution, if I can find a solution to this system. Now, we need to go back to all your knowledge on systems of linear equations. Because if I look at this system and I say let a be the coefficient matrix of the system, then I know A is equal to the matrix 4 minus 1, 1, 2. Then I know the determinant of A tells me something about solutions of that system. The determinant of this matrix A is 8 plus 1 is 9, and I know that's non-zero. So therefore the system is consistent. Meaning you can find A inverse and use A inverse to find A. You can use Cramer's rule, to find X and A and B. You can use Cramer's rule to find X, A and B. You can use Gaussian elimination to find A and B. You're going to find an A and a B that satisfies the system. So my knowledge on systems of linear equations tells me something about solutions of the system. So this means I can find an AB. Therefore, A and B exists. I can find them. It doesn't matter what they are, but I can find them. And therefore, I can say that the span of this set S is the whole of R2. Because I took an arbitrary element from R2 and showed I can write it as a linear combination. We didn't calculate the values of A and B because it depends on what X and Y I choose. But our knowledge on systems of equations helped me show that I will be able to find an A and B. Irrespective of what X and Y is, I will be able to find A and B. All right, let's look at this next example. This is a subset of R3. 1, 2, 3, 0, 1, 2. If I look at this and I say, well, can I look at the span of this set S? The span of S I know is all linear combinations. The set of all linear combinations, so it's A times 1, 2, 3. Plus b times 0, 1, 2, where a and b are real numbers. So the set of all those linear combinations, that's the span of S. So we can generate some elements from the span of S by picking various values of a and b. And I said R2, this is a subset of R3, So if we look at R3, the question is, if I take any x, y, z in R3, can I write it as a linear combination of those two? So the question is, can I find an A and B such that A times 1, 2, 3 plus B times 0, 1, 2 is going to give me X, Y, Z? So it means we're looking at the system A plus 0B is equal to X. 2A plus B is equal to Y. And 3a plus 2b equal to z. So now the question is, can I find this a and b? Well, if I set a equal to x, that we get from our first equation, b must then be equal to y minus 2x. Well, b here is dependent on a. So as a changes, b changes. So that means it wouldn't work for an arbitrary x, y, and z because they're dependent on each other. They depend on each other. I'm not even looking at z because I can already see. So I can see that the span of S is not going to be the whole of R3. The span of S is going to consist of an infinite number of elements, but not the whole of R3. So the question is, can you find something in R3 that's not in the span of S? Yes, you can find something. Find a x, y, z where it doesn't meet those conditions and it will work. All right. So If V is a real vector space, just some theorems relating to a theorem relating to span. If I've got elements of a vector space, that span of those vectors is going to be a subspace. So the span of the set W is not necessarily a subspace, but the span of all the elements. Well, if W is a vector space, but the set with just V1 to Vr is not a vector space, but W is a vector space because it's the span of those vectors. It's a vector space. It'll be a subset. It's closed under addition and scalar multiplication, and you can show that. But even more interesting is that span of that set is the smallest subspace containing those elements. Now, by smallest, I mean if I find another subspace that has the elements V1 to Vr in, that's a subspace, so it's a vector space, then W will be a subset of that set. So just to note, Pn, if Pn is a span, if this is Pn, we know is all polynomials of degree n or less, that's going to be the span of the following set, because I can write any polynomial a1 plus, let's start with a0, a1x plus a2x squared, all the way to an x to the power n. I can write any polynomial as a linear combination of those vectors. So Pn is the span of that set. So we're going to talk more about span, but from here we're going to have to look at linear independence, and then we're going to do some examples including linear independence, but also we're going to look at more examples of testing span and what the span looks like in the next videos.